All right. So this is, again, about online learning, but it's going to be a slightly different problem. So this slide is identical. We're still doing online learning. OK, great. So the classic online learning regret bound is norm of W star times G times square root of T. And we can get this using online gradient descent. And if you do this, you'll have to tune the algorithm, the learning rate of online gradient descent will have to tune to both W star and G. Okay? What if you wanted to get rid of some of this knowledge, or you want to have sort of a more adaptive algorithm? Well, there's a lot of work on this. Let's say if you don't know W star, but you know G, basically like the algorithms I talked about in the previous talk, you can do this pretty well. You sort of maybe get some extra log factor, but otherwise things are pretty good. Similarly, if you know G but don't know W star, again, you can get this up to some extra constant factor or something like this. If you don't know anything, things are a little bit sad. It turns out there's this lower bound that says that you can get sort of what you want plus some penalty, which is potentially exponential in time. I mean, in reality, it's maybe a little better. It's more like exponential in the rate of growth of the gradients. But if the gradients grow fast enough, it can be e to the root t. Right? So this seems really sad, right? Like maybe we should all, the math's proven that the world is unfortunate. We should all go home. But of course, in reality, things are not like this, right? People tune models all the time, and they don't know W star, they don't know G, and yet somehow our deep learning processes work, right? Like there's no exponential and root t penalty. So this suggests that this penalty is somehow unrealistic. And we can look at the lower bound proof to see sort of why. The first thing to notice is that the penalty is independent of W star. And if you look at the adversarial sequence that produces this penalty, it actually requires you to consider extremely large values of W star, right? And maybe in reality, W star is just not that big. So perhaps we should consider a different penalty that is maybe not independent of, that is independent of T, but depends on W star, so that we can sort of capture the fact that, we hope that W star is not that big, but we do in fact expect T to be quite large in reality, right? So sort of the end goal would be to have something like this. The average regret would be something, roughly speaking, like what we want. So linear on W star, linear on G, proportional to 1 on root T, and then some penalty that divides by T. And the idea here is that if the penalty is independent of T, this sort of second term is going to be kind of subasymptotic. For large enough T, it'll go away. And maybe it depends poorly on W star, but if W star is sort of reasonable, it won't look too bad. OK, so how are we going to do this? So we're going to start with an algorithm that knows G, but not W star, because these things exist, as I mentioned before. And then we're going to use a sort of series of kind of silly hacks to make it a little bit better. Okay, so the first hack is we're going to have these kind of what I call like just-in-time bounds, where we sort of interpolate between knowing G in the beginning and kind of knowing G a little bit at a time. And I'll explain that in more detail in a minute. Then we'll show that we can actually sort of lie to the algorithm a little bit to provide it with a guess of what G should be. And then you have to question how bad is that lie. It turns out that the lie is sort of OK. There's the third hack that will kind of show us that we can effectively give up on W stars that are too big, and everything will be mostly OK. OK, so let's go into this in more detail. So let's sort of consider an alternative sequence where instead of getting the value of G, the maximum gradient I'm going to see at the very beginning, what if I'm sort of just one step ahead of the algorithm, of the adversary? That is, I get a sequence of hints, HT, where I get HT before I prick my teeth iterate, and HT is an upper bound of the norm of GT. Then if you don't care about being scale-free, if you don't care about suffering like an extra log penalty or something like that, it's essentially trivial to hack together an existing algorithm and get something, a regret bound that looks like this. So it's the bound I want, W star G root T, and then W star times HT. So as long as these hints aren't growing too fast, everything will be OK here. All right. But we don't actually have these hints, so what should we do? Well, I think we do kind of what the natural thing to do is. If you were actually coding up this algorithm, you wanted to use it in a real application, you don't know what these hints are, what would you do? You would just make the hint be the biggest thing you've seen so far, right? That's probably reasonable. The gradients probably aren't getting that much bigger over time. Seems OK. So in reality, this could, maybe not in reality, but in theory, this could go horribly wrong if the hints are a little bit wrong even, right? So if HT is ever less than GT. So in order to fix this, we're going to lie to the algorithm again, right? We lied once, but as you know, if you lie once, you have to keep lying to support the lie. So we're going to give a truncated gradient G hat, which is just truncate the gradient so that it in fact is less than the size of the hint, right? So now there's a sort of issue where we've lied to the algorithm. It has good regret on the G hats, but maybe that has still bad regret on the actual Gs. turns out things are okay as long as the algorithm is sort of stable. So if the iterates of the algorithm are all bounded by some bound b, we can show that things are kind of okay. And it looks a little bit complicated, but I assure you it's not that bad. So we just write down the regret, and then you can decompose the regret into two terms. One is the first term is just the regret on g hat, which we have control over because the g hats are respecting the hints. And the second is that sort of error term that we experience. And the idea is that the error term actually telescopes, because we're sort of, just by Cauchy-Schwarz, we're kind of integrating up the total error of using the biggest possible gradient. And so overall, we're just going to have a sort of error term that looks like g times b in the end, which is not growing with t, or not obviously so. Okay, so now what we've got that if we do these hints things and we do this sort of weird hack, if the iterates are sort of stable, everything is okay. So let's just make the iterates kind of stable. So we're just going to constrain WT to be less than some bound b for some pre-chosen b. Turns out you can do this without affecting the regret bound at all. And then I'm going to choose b as square root of t. I chose that because it looks somewhat nice, but you can choose other types of b, like cube root of t or whatever. There are many, many possible things you can choose that are sort of reasonable. But let's do square root of t for now. All right, so for this, I have a picture proof of what's going on. So here's what's happening. There's sort of two possibilities. Either w star is less than b, or the normal w star is less than b, it's inside the circle, or it's not. If it's inside the circle, everything is okay, because now we can use the sort of regret bound that we had before, because w star is sort of inside the range of place that I'm exploring. And so we'll have, because b is square root of t, it'll be ordered square root of t, and we'll have like an extra plus 1, that, which is what I mentioned before. This is why you might consider a cube root of t, is so you can get rid of the plus 1 perhaps. If w star is too big, we're just going to give up on it. But it turns out to be okay, because we can write the regret at w star as the regret at 0, which I know about, because 0 is less than b, and it's actually a constant, plus something that's linear in w star and times t. That seems bad until you realize that I actually picked w star to be really, really big. So I can do some algebraic jujitsu, and t becomes w star squared, and we'll end up with a penalty that's w star cubed. So this is a little bit of a sleight of hand, but the right thing to do is, of course, to have a varying constraint set. So if you run the algorithm for an unknown number of time steps, you can make the constraint set kind of get bigger over time. And then you'll have this regret bound sort of uniformly for all time. Okay, so let me just sum up. We designed an algorithm whose regret bound is w star plus 1 times g times square root of t plus this w star cubed. So the idea is that we replace the e to the root t with the polynomial w star cubed. That seems nicer because exponentials seem really scary and polynomials for some reason are really great. But in practice, this may be more reflective of real problems, because you expect that square root of t is not really what's happening, even though t is really large, but w star may not be that big. Our two techniques were to do this truncating gradients and to constrain the predictions to a ball that makes the algorithm more stable. That's it. Thank you. It's a great question. I don't. I really like to. I feel like it might not be, but I don't know the right thing there. So this one, it will work in convex optimization, because you can just take the subgradients of the convex things and you'll get something. No.
So the next speaker is, if you want it, is Zach from University of Australia. Is that right? Yes. Could you speak about Lipschitz?
Okay, so this work is actually kind of like a follow-up from the previous talk. So we essentially use this gradient truncation trick as a first step to add Lipschitz adaptivity to some